Okay, guys, today we're going to look at how concentration of the reactants will affect the reaction rate. So how the concentration affects rates. Before we start, I need you to have a couple of things out. Obviously, you need your Chapter 5 guided notes. There's a lot of notes to fill out through today's lesson. And you're also going to need a calculator. Please make sure, if you're watching the video, please have a calculator out and ready to go. Okay, so let's get started. So far in this chapter, we've looked at how the reaction rate is influenced by the stoichiometry. And we did that with the rate expression. But now we're going to look at how the rate of the reaction is influenced by the concentration of the reactants. And this is going to be looking at the rate law. Okay? So a couple things there. We looked at before how stoichiometry affects the rate of a reaction, and we called that the rate expression. Today, we're going to look at how concentration of the reactants will affect the rate, and we're going to call it the rate law. Most reactions are reversible. If you remember what a reversible reaction is, it means that over time the products can begin to turn back into the reactants, and this complicates our calculations. For example, if we have this reaction A plus B and it's reversible and it goes to C. If you think about reaction rates, we're interested in how fast A and B make C. But guys, if C can decompose back into A and B, that's going to complicate things. So what we will do, to make the calculations easier, we will look at the rate of the chemical reaction when the reaction first begins. So when this reaction first begins, and we call that rate the initial rate. So right when you put A and B together, and you mix them, we're going to look at the rate of the reaction right when you do that. It's called the initial rate. Okay, so rate law, that's what we're going to talk about this whole lesson. You need to write down the definition. Rate law is an expression which shows how the rate depends on the concentration of reactants. So how the rate depends on the concentration of the reactants. If we have this chemical reaction, we've looked at this one before, 2 moles of nitrogen dioxide decomposes to 2 moles of nitrogen monoxide and 1 mole of oxygen. This would be the rate law right here. The rate of this reaction is equal to K times the molar concentration of nitrogen dioxide raised to some exponent here they're calling N. Before we start, I want you to write this in the margins somewhere. When you see brackets in chemistry, that is telling you something. That is telling you the concentration in terms of molarity. So this is the molar concentration of this reactant. Now I wanted to point something out to you. The rate law is only concerned about the reactants. We don't care about the products. So you're only going to build in the molar concentration for the reactants in the rate law. We will look at the rate and concentration data from actual experiments in order to determine the rate law. So we're going to go through a lot of actual experimental data to determine these numbers that will be plugged into the rate law. Okay, but before we do that, we must master the lingo of the rate law. Lingo means the terminology that goes with the rate law. So let's learn how to know all of the terms that are involved in this rate law. So if we consider this reaction, A plus B goes to X. The rate law for this chemical reaction would be right here. So this would be the rate law. Notice the rate is equal to K times the molar concentration of A, that's a reactant, raised to some power, they're calling M, times the molar concentration of B. This time we have 2 reactants, so we've got to have two reactants in the rate law, raised to some power n. Now let's explain what each of these terms mean. Where you see K in the rate law, K is the rate constant. It's known as the rate constant. Where you see brackets around the A, one of our reactants here, it means the molar concentration of that reactant. It's the molar concentration. So the concentration in terms of molarity. Where you see the brackets around the B, that's the molar concentration of the other reactant. Now, you see some exponents here. The molar concentration of A is raised to the exponent, which they call M. M is the order of the reaction with respect to A. So M is the order of the reaction with respect to A. N, also this exponent, it is the order of the reaction with respect to B. That's how a chemist would say that. It is the order of reaction with respect to B. Now, if you notice something, I just called the exponents orders. And they can be 0, they can be whole numbers, or they can be fractions. But they must be determined by actual experimental data. So you're going to run reactions and you're going to determine what these orders are, what M and N are. And that's what we're going to do today. I'm going to show you how to do that. The rate constant, K, is temperature dependent. Guys, what happens to the speed of a chemical reaction if you increase the temperature? Yeah, the speed of the reaction goes up. It occurs faster at higher temperatures. So K is temperature dependent and must be evaluated by the actual experiment. Okay, here's an example of a rate law. Let's talk about this for a second. Rate is equal to the rate constant times the molar concentration of A raised to this exponent of 1 times the molar concentration of B raised to this exponent of 2. The overall order for this reaction is simply the sum of all the exponents. So if we take these exponents, what's the sum of these exponents, guys? 3. 1 plus 2 is equal to 3. So the overall order of this reaction would be 3. Pretty easy. Very easy. We are going to study the following orders of reactions. We're going to study a 0 order reaction. Remember that order is the exponent. So when the exponent is 0, we call it a 0 order reaction. We're going to study first order reactions. So when the exponent is a 1, that would be called a first order reaction. And then finally we'll look at second order reactions. So when the exponent is a 2, that is a second order reaction. Now, the following slides, we're going to examine each one of these orders in more detail. So we're going to first look at 0, then go to first order reactions, and then second order reactions. So let's start. 0 order reaction, here is the definition. In a 0 order reaction, the change in the concentration of the reactant has no effect on the rate. So think about that. The change in the concentration of a reactant would have no effect on the rate. These are not very common. Most of the time, when you change the concentration, if you increase the concentration, it's going to increase the rate. So 0 order reactions are not very common. The general form for the rate law for a 0 order reaction is rate is equal to the rate constant. So I want to talk about 0 order reactions for a second. If this is the rate law, it's equal to the rate constant times the concentration of some reactant raised to some power. In a 0 order reaction, what is the exponent going to be right here? It's going to be a 0. So let me show you how the math of this works. What if we took the concentration of this reaction and we times it by 2? So I'm going to put a times by 2 in here in this concentration box. But if I raise it to the 0 power, because it is a 0 order reaction, how is that going to change the rate? Yeah, what is something raised to the 0 power? It's equal to 1. So this isn't going to change the rate. And so that's why it says here, the change in the concentration of the reactant has no effect on the rate. And when you write the rate law, if it's to the 0 power, a chemist would never write it to the 0 power. They just leave this term off. And so the rate law is equal to, the rate is equal to K, the rate constant. Okay, let's look at first order reactions. Here's the definition. A first order reaction is the rate is directly proportional. So the rate is directly proportional to the reactant's concentration. What does that mean, directly proportional? Well, here's what that means. If I was to double the concentration, how will that affect the rate? Well, if it's directly proportional, it's also going to double the reaction speed or the reaction rate. Okay, so they're directly proportional. If you double it, it doubles the rate. What if I triple it? It triples the rate. Okay, these are very common chemical reactions. Think about it. In terms of collision theory, if you've got more molecules because you've increased the concentration, isn't that increase the probability that they're going to collide, react, and form the product? Sure. This is how most chemical reactions will occur. The general form for a first order reaction, the general form for the rate law is rate is equal to the rate constant times the concentration of some reactant raised to the first order. That's what makes it a first order reaction. Let me show you the mathematics of it and see if it makes sense. So if this is my rate law, we've got some reactant here. It is a first order reaction, so that's a 1 right there. Would I need to write the 1? No, it's implied, isn't it? 1s are implied. But let's say I take the concentration and I times it by 2. How is that going to affect the rate? If I times this by 2 and then raise it to the power of 1, what does that become? It's still times by 2. So the rate would also be times by 2. Does that make sense mathematically? What if I didn't double it? Let's say I quadrupled it. So let's say I times it by 4. If I times it by 4, raised to the first power, that's still times by 4. So notice, in first order reactions, the rate is directly proportional to the reactant's concentration. All right, finally, we'll look at second order reactions. Here's the definition. Second order, the rate is quadrupled when the reactant's concentration is doubled. So we'll think about that. The rate is quadrupled when the concentration is doubled, and increases by a factor of 9 when the concentration is tripled. Second order reactions are very common, especially for gas phase reactions. Remember when we introduced kinetics and reaction rates at the very beginning of this chapter? Which phase, solid, liquid, or gas, will react the fastest? Gas phase. There's more surface area for these molecules. They're flying fast. They're going to collide faster. They're going to react faster. So they're very common gas phase reactions, second order. The general form for a second order for the rate law would be this. So the rate is equal to K, which is the rate constant, times the molar concentration of A raised to the second order. So again, guys, it's this exponent right here that determines the order of the reaction. Now let's look at the mathematics of a second order and try to make sense of this. So if this is my rate law, it's equal to K times some molar concentration of my reactant raised to the second power. What would happen if I doubled the concentration of that reactant? Well, 2 raised to the second power is what? That would be now times by 4. So my rate would be times by 4. So the rate is quadrupled, or times by 4, when the concentration is doubled. Now, what if I didn't double it? Let's change the numbers now. What if I times the concentration by 3? 3 squared is what? Times by 9. So my rate would increase by a factor of 9 if I tripled it. Okay, so let's summarize what we just talked about. Let's summarize the rate law lingo. For this reaction, okay, now I've got a new reaction here. I've got that chemical reactions going on. The rate law for that reaction would look like this. It would be some rate is equal to the rate constant. I've got reactant A, so this is the molar concentration of A raised to the order of M, times the molar concentration of B raised to the order of N. All right, so I want to show and go through some examples of what a chemist would say. For example, if M equals 0, so this exponent equals 0, here's how a chemist would say that. The reaction is 0 order with respect to A. So if this was a 0, it's 0 order with respect to A. Now, what if M was 1? A chemist would say the reaction is first order with respect to A. This was a 1, it's first order with respect to A. And of course, if M was 2, a chemist would say this was a second order with respect to A. Now let's look at N. N is our exponent over here. How would a chemist say that? If N was 0, the reaction is 0 order with respect to B. If N was 1, a chemist would say this reaction is first order with respect to B. And obviously, if N was 2, a chemist would say it's second order with respect to B. I want you to get used to saying it like that. That's how I'm going to say it, and I hope that you will get used to saying it that way as well. Now, what if M was 1 and N was 2? What would the overall order of this reaction be? 3. How do you get that? You simply are adding or taking the sum of the exponents. 1 plus 2 is 3. So it would be a third order overall. Okay, practice problem number 7. I've got a bunch of practice problems coming up. For this reaction, A plus B plus C goes to some product. Remember, with the rate law, we're not concerned about the product. So it didn't tell us what the actual product was, but we don't care. We're just concerned about our reactants here. If this was the rate law, okay? If this was the rate law, I'm going to go through these questions with you on practice problem number 7. Let's go through part A together. A says, what effect does doubling the concentration of reactant A have on the rate of this reaction? Good. If we doubled this, we times this by 2, but raise it to the 0 power, what's anything raised to the 0 power? What is that? It's 1. So would it change the rate? No. So there's no change. And that's how I would answer that one. Okay, let's go to part B. It says, what effect does doubling the concentration of reactant B have on the rate of the reaction? Good. So now we're at reactant B. If we double this one, raise it to the first power, that's also going to double the rate. So I'm just going to put it doubles the rate. Remember, in first order, it's directly proportional. So if you double the concentration, you're going to double the rate. Now, reactant C is second order. So this is second order with respect to C. Let's see how that would change things. Part C says, what effect does doubling the concentration of reactant C have on the rate of this reaction? Yeah, so now if I put a times by 2 in right here for C, we're squaring it. So 2 raised to the second power is what? 4. So we're really going to take the rate and times it by 4 or quadruple it. I'm just going to put times by 4. Okay, let's see if we got that right. On A, it had no effect. B was double the rate, which we got. And C was quadruple the rate. Does that make sense, guys? Not too bad, right? I've got another practice problem. I would like you guys to try this one on your own. So practice problem number 8 has part A and part B. So let me give you a second. This is the rate law. You're going to look at that and answer part A and B. If you're watching the video, please hit pause at this point, answer A and B, and once you have an answer, then hit play, see if you got it right. Okay, so hopefully at this point you've tried it, and you have an answer for part A and B. Let's see how I would approach a problem like this. Let's just go to A. It says, what are the reaction orders for this reaction? So here's how I would answer part A. With respect to the reaction NO, what order is it? It's second order, so I would say it's second order with respect to NO, nitrogen monoxide. But there's also another reactant here. We've got hydrogen. What order is it with respect to hydrogen? Now, they didn't write anything, but what's implied? A 1 is implied there, so it's first order with respect to hydrogen. So that's how I would write it. Okay, and then let's look at B. It says, does doubling the concentration of NO have the same effect as doubling the concentration of H2? And the quick and easy answer is no, it doesn't. But let's look at how they're different. What if I double NO? Well, it's a second order, so that would actually increase the rate by 4 times. So NO would increase the rate by 4 times. What if I doubled hydrogen here? There's a 1 here, so it's just timesing it by 2. So hydrogen would increase the rate by 2 times. So no, it's not the same. Okay. Let's see if we got it right. Kind of wrote over the top of that, but yes. Oh, overall, we didn't do that. What order is this reaction overall? 2 plus 1 is what? 3. Is 3. So it would be third order overall. And yes, we got part B right. Okay. Making sense? I hope so. Stay with me. Stay with me. Now we're going to look at something different. And this is where it starts to get a little more complicated. We're going to look at how to determine reaction orders. How do we actually determine what those exponents are going to be? Whether it's a 0, whether it's a 1, or whether it's a 2. Reaction orders have to be determined experimentally. So we're going to be looking at experimental data. And I'm going to teach you how to look at those data tables and determine what the order of the reaction will be. We're going to look at actual experimental data to determine them. Let's go to the example problem. This is in your guided notes. I would like to see you guys write down on this example problem everything that I'm about to write down. This is a little more complicated, okay? So rate law example problem, let's get to it. It says write the rate law. So I need to write the rate law expression for this reaction. A plus B goes to some product. And it says, for this example, I will show you how to use table logic. That's what I call it. we're going to use table logic. You might hear me say that a few times in order to write the rate law. So, before we start, I think you guys have a good idea of how to write a rate law. I want you to write this down. This is the rate law. Rate is equal to the rate constant times the molar concentration of A, because we have a reactant called A, and my other reactant is B. But we're going to raise A to some power. It's going to be some order. It's going to go there. Then we're going to times it by the molar concentration of B raised to some power. So the order with respect to B will go right there. Our job is to use this data table here to determine what numbers go here. Does that make sense? Now, this is the first time that we've gone through a problem like this. There's a huge data table. Let's go through and look at what the data table is reporting. It looks like to me the experiment number, they did this experiment how many times? They ran it 5 times. This column is the initial rate. So this is the rate of the reaction. How fast it's going. This column is the initial concentration of reactant A. So this is the concentration of reactant A. What are they doing here, guys? In every experiment that they ran, they kind of messed with the concentration of A, didn't they? So they're running it at different concentrations. And also, the last column is the initial concentration of B. And it looks like sometimes they keep it constant, but they are messing with the concentration of B. Okay, here's table logic. Let me show you how to do this. It's very easy if you'll pay attention. If we want to determine the order of this reaction with respect to A, we need to control B. So where do you see on this data table experiment 1, 2, 3, 4, and 5, where do they hold B constant? 1, 2, and 3 is all held constant. And that's what we want to look for. We want it to be controlled for B. We don't want it to be changing. We want to notice where A is changing, and then we can relate the change in rate to that reactant, A, instead of B. Okay, so here's what I do. If 1, 2, and 3, they're not changing B. Now let's look at A. Where do you see in the experiments where A is doubling?
1 and 3.
1 and 3. Perfect. So what I would like to see you guys do is draw a bracket between 1 and 3. Okay, a bracket like that. And what I do, since it doubled, is I just put a times by 2 sign there. Now, I would like to see you draw a bracket between 1 and 3 for the concentration of B. And this didn't change, did it? So I put control. An experimental control is just that. It doesn't change. This is being controlled. Now, let's look at the rate between 1 and 3. So draw a bracket between 1 and 3. How did the rate change there, guys? There's no change. So I would just put no change. Now we got to think about those reaction orders. 0, first, or second order. If we change the concentration, we in fact doubled it, but it didn't change the rate, what order is that? 0 order reaction. So with respect to A, because we doubled that one and it didn't change the rate, it's 0 order. So what am I going to write right here?
0.
A 0. It is 0 order with respect to A. Now stay with me. We're going to go through a lot of these. Okay. Let's. What I would like to do now is erase, just to make it clean. We figured out what the reaction order was with respect to A. So I'm going to erase all of this stuff I wrote on the table. You guys can, yes, if you would like to. If it cleans it up a lot easier, because we're going to write more on this table. So now we'll do the same thing, but now we want to determine the order with respect to B. So who do we have to control now? A. Is there a spot where A is being controlled but B is doubling?
Yeah.
1 and 4. Let's look at 1 and 4. Yes, perfect. So if you look here between experiment 1 and 4, what are we doing to the concentration of B? Timesing it by 2. So put a bracket and put times by 2. Now why we picked 1 and 4 was because A, what's happening? It's not changing. So this is my what? That's my control. You could have picked 4 and 5, but it would have been more difficult because this isn't really doubling, is it? No. So it's better to pick 1 and 4 here. Yeah, always look for where it's doubling. That makes the math easier. Now, if we look at the rate between 1 and 4, draw a bracket there between 1 and 4. What's happening to the rate? It's doubling. Yeah, if you took 0.5 and doubled it, you would get 1. So let's also put times by 2 right there on the rate line. Now this is where you gotta do some thinking. If you double the rate, you double the concentration, and it also doubles the rate, what order is that? That is first order. Okay, so what am I going to write right here? A 1. Okay, and now we're done. But let's clean this rate law up because this is not how a chemist would write it. Here's how a chemist would write the rate law. So this is the answer. The rate is equal to K, which is the rate constant. Now, anything raised to the 0 power is 1. Do I need to include that in the rate law? No. And so a chemist wouldn't even put that in. Okay, and then we've got the molar concentration of reactant B raised to the first power. Do I need to write a 1? No. So there is how a chemist would write the rate law for this reaction. Does that make sense? Okay. Did we get it right? The rate is equal to K times the molar concentration of B. Correct. Okay, practice problem number 9. It's almost exactly the same. There's a little bit of differences though. Let me walk you through the differences. It says determine the rate law. So again, we're going to write the rate law. But it also says, and this time we're going to determine the value for K. The rate constant, we want a value for K. And I'll show you how to do that for this reaction. Now let me go to the data table. It's almost the same, but it's a little different. We've got experiments. How many times did they run the experiment? 4 times. Now on this data table, they listed the concentration first. So the concentration of NO2 and the concentration of CO, and the rate of the reaction they put on the right column. A little bit different. What I would like you to do now is to go through and figure out the order of the reaction with respect to both of those reactants. So everyone write down this first. Rate is equal to K. We're going to write the rate law. We have 2 reactants. The molar concentration of NO2 raised to some power times the molar concentration of CO raised to some power. What I want you to do is use table logic now and figure out the order of the reaction with respect to those reactants. If you're watching the video, please hit pause. Once you get the orders down, I will show you how to calculate the rate constant. So if you're watching the video, please hit pause. Try to get the orders of the reactants, and then once you have your answers, hit play and see if you got it right. Okay, let's see how you guys did. Hopefully you have an answer for what the orders of this reaction are with respect to each of those reactants. Let's go through it, and here's how I would approach this problem, okay? If I'm trying to determine the order with respect to NO2, I want to make sure that CO is controlled. So I want to look for a spot where CO is not changing, but NO2 is doubling. Where is that, guys? Where NO2 doubles, but CO is remaining constant. 1 and 2. Yeah. This one is doubling while CO is not changing. What do we call this one then? That's my control. Now, let's look at how the rate is changed. When I double the concentration of NO2, how did that influence the rate? Guys, if you easy way to figure this out, always take the larger number and divide it by the smaller one. So if you take 0.0082 and divide it by 0.0021, what do you get? It's 3.9. But guys, you got to remember, this table is actual experimental data. 3.9 is essentially what? 4. So I'm going to say times by 4. Okay? So now you've got to really think about it. Yeah. If we double the concentration of N2, and that quadruples the rate, what does this exponent have to be in order for this rate to be times by 4? It would have to be a 2. Because 2 raised to the second power is 4. And that's why it's increasing the rate by 4 times. So that's how I would figure out the order with respect to NO2. Now let's clean up the table a little bit. I like to erase it after you figure out one of them. I'm going to erase this stuff. Clean up the table a little bit. And now let's figure out the order. Maybe. Let's figure out the order of this reaction with respect to carbon monoxide. I want to look for a spot where carbon monoxide is doubling, but NO2 is now held constant. Which experiments do that? 2 and 3. Yeah, if you look at 2 and 3, I want you to draw brackets there and put times by 2. We're timesing the concentration of Cl by 2, but look at what happens to the concentration of NO2. It remains constant, so this is my control. So I just write control there. Now let's look at how that affected the rate. When I doubled the concentration of carbon monoxide, how did that affect the rate? Yeah, these two numbers, I'm hoping that you're recognizing that it's essentially the same number. I mean, there's tens, hundreds, thousands. This would be 10,000s. There's 1 10,000th difference. You've got to realize these are actual experiments conducted in a lab. When you do this in a lab and you get 1 10,000th difference, there's no change. Statistically, no change. So I'm just going to put no change. Now think about it. When we double now CO, but it doesn't have an effect on the rate, what does the exponent have to be here? A 0. So that is 0 order with respect to carbon monoxide. Perfect. Now let's write the rate law. So the rate is equal to K times the molar concentration of NO2 raised to the second power. Now, would a chemist include CO? No, because it's raised to the 0 power, it's going to be 1. So this would be how a chemist would write the rate law. So that's the first part. We just calculated the rate law. Now, very important, I'm going to ask you now to calculate the rate constant. I want a value for K. Here's how you do it. It's very easy. You can pick any of these 4 experiment numbers. I always pick the first one. So I just kind of box in the first one. And we're going to use those values. But could you use 2? Yes. Could you use 3? Yes. Could you use 4? Yes. And it would get the same answer. Now we're going to use experiment number 1 and just plug in. Do we know the rate for experiment number 1?
0.0021.
Yeah, the rate was over here. It's going to be this number, 0.0021. I'm going to plug that in down here, 0.0021. And I'm just following the rate law. It's equal to. Do I know K?
No.
Nope, so I'm just going to write the value or the letter K in there. Now, do I know the concentration of NO2? For the first experiment, NO2's concentration, 0.1. So 0.1 goes in right there. But what exponent am I using? It's got to be a 2, because this was second order with respect to that. Now I have a mathematical equation, simple equation with one unknown. You've got to solve for what K is. So let's do that. What I would do first is square 0.1. And when you do that, you get .01. Now, how do we get K by itself, guys? Yeah, you want to get rid of this 0.01, so let's divide it by 0.01. And let's do that to both sides. Over here, it cancels out, and that's what we wanted. So K is equal to 0.0021 divided by 0.01. So K is equal to, did you guys get this? 0.21? Okay. But that's not all. What are the units for K? This gets a little complicated, but I want you to think about it. Let's do some analysis of the units here. The rate, so when it says rate is equal to K times NO2 raised to the second power. Rate is in units of molarity per second. So let's put the units in, molarity per second for the rate. K, we're trying to determine what the units should be. So let's just write K. What is this in brackets? What is that really?
Molarity.
Molarity. But we're squaring it, so that's going to be molarity squared. Now, what does K have to be in order, when you times these together, that it equals molarity per second? What would K have to be? Wouldn't K have to be equal to 1 over molarity seconds? Wouldn't it have to equal that in order to times it by m squared? When you times it by m squared, now this molarity cancels out with one of these, and so you're left with molarity on top divided by seconds. Okay, so there's your answer. And a chemist would most likely write it like this: molarity to the minus 1, seconds to the minus 1. Remember that minus 1 just means it's 1 over that. Do you want an easier way of figuring that out?
Yes.
Okay, here's an easier way. If you look at the overall reaction order, what was it here? 2. That was our only one, it was 2. How to figure out the units of K? You just subtract it by 1. What's 2 minus 1? It's 1. And so you put a little minus sign in front of it. So 2 minus 1 is 1, and then you just got to remember to put a minus sign in front of it. So it's a molarity to the minus 1, and seconds is always going to be to the minus 1. Your time value has got to be on the bottom, so it's going to be seconds to the minus 1, always. Okay. It'll make sense. We'll go through a lot more practice problems.
The molarity number can change at the top?
Yeah, these units for K will change. The units for K will change. Okay, I've got, that was practice problem number 9, so I got 10, 11, and 12. I've got 3 more practice problems. Did we get that one right?
Yeah.
Yes, we did. Okay. Practice problem number 10. It's exactly like number 9. I want you to write the rate law and calculate the rate constant. Here's your experimental data. Let's have you guys try this one on your own. See if you can get it. So if you're watching the video, please try it. See if you can't solve for both the rate law and the rate constant. So hit pause right now. Try it. Once you have your answer, hit play and see if you got it right. Okay, so hopefully at this point you have an answer for both what the rate law is and the rate constant. Here's how I would approach this problem, okay? Let's write the rate law first. So the rate law looks like this. Rate is equal to the rate constant. Now it looks like we have two reactants. So I'm going to times it by the molar concentration of the first reactant, which is NH4, plus, raised to some power. We don't know it. We'll figure it out. Our other reactant is NO2. So we're going to times it by the molar concentration of NO2, raised to some power. That's how you should begin the problem. Now let's use table logic, looking at this data table, and figure out what goes on our exponents here. If I want to determine the order of the reaction with respect to NH4, I want to look and see where NH4 is doubling, but NO2 is remaining constant. It's being controlled. What experiment number should I look at?
3 and 4.
Where NH4 is doubling,
Oh.
but NO2 remains constant. There's really not a spot, is there? So think of it this way. Is there a spot where NH4 is being times by 3 or tripling? Yes. And so if we look right here, NH4 is increasing by a factor of what? Well, it's times by 3. If you take 0.02 and times by 3, you get 0.06. NO is being held constant, so there's my control. And what's happening to the rate? Now be careful here. This rate is this number times by 10 to the minus 7. But how is that changing, guys? 10.8 and 32.3. It's essentially timesing by 3, right? So put a times by 3 sign there. Now let's look at it. If this one, the concentration is being times by 3, and it increases the rate by 3, what order is that? That is first order. So a 1 goes here. Again, if this is times by 3 and the rate is times by 3, in order for that to equal and make sense mathematically, that exponent's got to be a 1, which means it's first order. Okay, that's great. I'm going to erase that, what we just did, clean up the table a little bit, and figure out the other one. Okay, so now I'm looking at determining the order of this reaction with respect to nitrogen dioxide. I want to find a spot where nitrogen dioxide is increasing, but NH4 is being held constant. What should I look at? Three and 4. I agree. Okay, if you look here, how much is the concentration of NO2 increasing? Isn't that by 2? It's exactly 2. So I'm going to put it times by 2. And you'll notice that the other reactant is being held constant. So this is my control. So I like to see you guys write those things. Draw the brackets and write control there. Now let's look at how the rate is changing. Guys, essentially, what is the rate doing? It's doubling. Yeah, if you take 10.8 and times it by 2, it's going to be very close to 21.6. So I'm going to put a times by 2 right there. Now we got to think about it. If you double the concentration of NO2, so I double that one, what exponent would have to go there so that we also double the rate? A 1. So that is first order with respect to NO2. So now let's write the rate law. The rate is equal to K times the molar concentration of NH4. Now would a chemist write a 1 right here? No, it's implied. They don't need to. Times the molar concentration of NO2. And again, do I need to write the 1? No. So there's the answer to the first part. Now, let's determine the rate constant. Now remember, can I choose any one of these experimental numbers? 1, 2, 3, or 4? Yes, what I always do, I just always do this, I don't know why, is I pick the top one. And I put a box around it. Now let's plug in the variables where they should go. What was the rate on this first experiment? Now remember, you got to keep this times 10 to the minus 7. So that's 10.8 e to the minus 7th is equal to, do I know K? Nope. What is the molar concentration for NH4? 0.02. So I'm going to take that and times it by 0.02. And I'm raising it to the power of 1, so I don't need to write it. Times it by the molar concentration of NO2, which is 0.2. Now it's a simple mathematical formula with one unknown. Let's solve for it. What I would do first is take 0.02 and times it by 0.2. 10.8 e to the minus 7th is equal to K times 0.004. Is that what you guys got?
Yeah.
Now, how do you get K by itself? Divide it by 0.004, both sides. Cancels out over here. And so K is equal to 10.8 times 10 to the minus 7th divided by 0.004. Okay, so if you do that, K will equal 0.00027. Now, in all of these rate law problems, we could be dealing with rates that are in very small numbers, and let's change this rate constant to scientific notation. So let's go ahead and put K is equal to 2.7 times 10 to the minus 4. Now, that's the value of K, but we also need to include the units for K. And this is where students get a little bit confused, so I'm going to try and make it easy. You do the overall reaction order. So there's a 1 here and there's a 1 here. That's 1 plus 1 is equal to 2 overall. So that means when you do the molarity, what we're going to do is take 1 less than that. So it's a 1, but we always have to put a negative sign there. So it's molarity to the minus 1 times seconds to the minus 1. You're always going to have your time value on the bottom, and so that's what that means. Okay, and so that's your rate constant. I've got a couple more practice problems here that I would like to go through. So let's see if we got that right. We did get our rate law right. It was correct. And the rate constant, K, was also correct. So very good. Okay, let's go to practice problem 11. Very similar, just another chance to see a problem like this. It says determine the rate law and the rate constant. So again, you're going to be solving for the rate law and the rate constant for the following reaction. Now look at this one. We've got 3 reactants here. So we've got to account for all 3 reactants in our rate law. So I'm going to ask you to solve this one on your own first. Start with writing the rate law and then determining the orders through table logic, and then determine the rate constant after you figure that out. So if you're watching this video, please hit pause at this time, work it out, see if you can't solve for the rate law and the rate constant. And once you have those answers, hit play and see if you got it right. Okay, so hopefully at this time, you've all tried it and you've got an answer. So I think that real learning is going to occur if you really try it on your own first. So here's how I would approach this problem. If we're going to go and determine the rate law, let's actually write the rate law here. So rate is equal to K. Now we times the molar concentration of all of the reactants. So we've got BrO3 minus times the molar concentration of Br times the molar concentration of H+. Now, what we need to do is figure out what the numbers are. I didn't leave enough room there. What the numbers are, the exponents. So what order it is with respect to each one of these reactants. And that's where table logic comes into play. And so let's go ahead and do that. So if I want to determine the order of the reaction with respect to BrO3, I want to find a spot where in my experiments, so I've got 4 of them here, where BrO3 is changing, but Br and H plus are held constant. And so let's look for a spot where BrO3 is changing, but the other two are held constant. Okay, so where BrO3 is changing, so it looks like it's changing here, and Br is held constant and H plus is held constant. I want you to draw in your brackets like this. What's happening between experiment 1 and 2? Well, the concentration of BrO3 is doubling, so I'm going to put it times 2 right there. This is a control. It's not changing. And this is a control. It's not changing. Now let's look at how the rate changes between those two. Now it's written in scientific notation. Remember, if it's to a negative number, we move the decimal to the left. So when it says -3 and -4, which one is actually the larger number here? And I'm hoping that you're thinking to yourself that this 1.6 times 10 to the minus 3 is a larger number. So if we want to figure out exactly how many times larger it is, we're going to take this number, 1.6 times 10 to the minus 3, and divide it by the smaller number. So divide it by 8 times 10 to the minus 4. And when you do that, you're going to notice it's exactly twice as large. So this number is twice as large as in experiment number 1. Okay, now when we have those numbers, we can think about this. So BrO3, if we times the concentration by 2, because that's what we're doing, and we hold these ones constant, and our rate is also doubling, what does the exponent have to be here so that it's still times by 2? Well, the exponent has got to be a 1. So it's first order with respect to BrO3. And that's how we figure that out. Okay, now what I'd like to see you guys do is kind of clean up the table before we continue. Let's clean up the table. So we're done with BrO3. And now let's work on figuring out the reaction orders with respect to these other reactants. So now let's move to Br. Now what we're going to look for on our table is where Br is changing, but where BrO3 and H plus are held constant. Okay, if we look here, Br is changing between 2 and 3, and it's doubling. And H is held constant, and BrO3 is constant. So these are my controls. And now let's look at how the rate has changed. Okay? And we look here, and it's both times 10 to the minus 3, so we can just look at the number out front here. And this is twice as large, so we're increasing this one by 2 times. So if you take 1.6 and times it by 2, we get 3.2. So that tells us something. Hopefully you're getting better at this now, but if Br is increasing by a factor of 2, and the other two reactants are constant, and my rate is also increasing by 2, what exponent would have to go here so that this 2 here equals 2? Well, hopefully you're thinking to yourself that it's first order. This would have to be a first order with respect to bromine. Okay. All right, now we've got the orders with respect to the first two reactants. Now we just got to get it with respect to H+. So again, let's clean up the table. So erase what we have written here. Okay, and now let's go ahead and use table logic to figure out the order with respect to H+. Now we want to find a spot where H+ is changing, but the other two reactants are held constant. So let's see if we can find it. Okay, if we look here at between 3 and 4, it's changing, but then Br is also changing, and so is BrO3, so that wouldn't work. So let's go, looks like we're going to have to go 1 and 4. It's changing by 2 with respect to, or the concentration is changing by a factor of 2, between experiment 1 and 4. And between 1 and 4, BR is not changing, so that's a good control. And also, BRO3 is not changing, so that is a good control. All right, now let's look at how the rate changes between those two experiments, experiment number 1 and 4. Now again, this is to the -3, so this is actually a larger number than the first one. So in order to figure that out, what I would do is put the larger number in your calculator first, 3.2 times 10 to the -3rd, and then divide it by the smaller number, 8 times 10 to the -4. And you'll notice that in your calculator it says 4, so what that means is it's 4 times larger. This number is 4 times larger, so the rate is increasing by 4 times. All right, so there's our table logic. Now we just got to figure this out. If the concentration of H plus is changing by a factor of 2, but the rate is increasing by a factor of 4, what exponent would need to be right here in order to get an answer that is 4? And hopefully you're thinking to yourself, well, that exponent's got to be a 2, because 2 raised to the power of 2 is 4. So with respect to H plus, this is second order. All right, so I'm just going to clean this up just a little bit. Let's erase, maybe. Let's erase this data that we just put in there. All right. So now let's go about answering this question. What is the rate law? So now we can write the rate law correctly. And here's what I would write. The rate is equal to the rate constant times the concentration of BrO3 times, and would I need to write the 1? A chemist will not write the 1. 1, 0 is implied. And so we're going to times it by the concentration of Br. And we're going to times it by the concentration of H plus. Now H plus was second order, so I do need to include that 2 right there. So there's my answer for the rate law. Now we can go ahead and actually solve for the rate constant. The rate constant is K. And remember, when we're solving for the rate constant at the very end, you could pick any one of these 4 experiments. It would all give you the same answer. But I always just choose to use experiment number 1. It's on the top. It keeps it nice and organized there. So I draw a box around experiment number 1, and we're going to plug in these values to the rate law and then solve for K. So let's do that down here. So my rate in experiment number 1, the rate was 8 times 10 to the -4. So 8 times 10 to the -4 is equal to, now what I'm doing is just plugging in numbers here. The rate was 8.0 times 10 to the -4. It's equal to, so I put an equal sign, K. We don't know the value of K, so I'm going to write K. Now I need the concentration in terms of molarity of BrO3. In experiment number 1, BrO3 had the molar concentration of 0.1. 0.1. It was raised to the first power, so I'm just going to keep it as 1 there, and let's go on. Molar concentration in Br, in the first experiment, was also 0.1. Again, it was raised to the first power, the first order, so I'm not going to write anything there. But I had another reactant, H plus. Its concentration was also 0.1. However, it was raised to the second order, so I need to write a 2 right there. Now we have an easy math equation with just one unknown. What I would do first is times all of these values together. So 0.1 times 0.1 times 0.1 squared. So 8 times 10 to the -4 is equal to K times 0.0001. Now, if we're solving for K, I need to get rid of this term right here. So let's divide it by both sides. over here it will cancel out and it leaves just K, is equal to 8. So let's put that in my calculator. 8 times 10 to the minus 4. And let's divide that by 0.0001. Okay, and if we do that, our rate constant K is equal to 8. Exactly 8. But what are the units for K? Now let's go back and figure out the overall order of this reaction was 1 plus 1 plus 2. So 1 plus 1 plus 2 is equal to 4. Now an easy way of determining the units for K, if we take the overall order of the reaction and subtract it by 1, that is equal to 3. So, and then we have to put a minus sign on there. So it's molarity to the minus 3. And where am I getting minus 3? That's how I got it. I just subtracted 1 from the overall order, and then make sure you include a negative sign. And the time, if you'll notice, the time was in seconds. And so seconds to the minus 1. And that will be your units for K. So hopefully you were able to get that correct and that makes sense. I've got one more practice problem for you to try. This is the last one of the lesson. And so, and yeah, we did get that one right. Let's go ahead and do practice problem number 12. It says determine the rate law and the rate constant. It's the same exact question for this reaction. We have 3 reactants again. So please go ahead and try this one on your own, okay? If you're watching the video, please hit pause at this point. Try to get the rate law and the rate constant correct. Once you have tried it and you have your answer, hit play and see if you got it right. Okay, so hopefully at this point you've tried it. But let me show you how I would approach this problem. If we're going to write the rate law for this reaction, I'm going to do that right up here. So the rate is equal to K, the rate constant, times the molar concentration of all of these reactants. So H2O2 raised to some power times the molar concentration of iodine, I minus, raised to some power times the molar concentration of H plus raised to some power. So there's my beginning rate law. It's not finished yet. I need to figure out the order with respect to each of these reactants. And that's where we're going to use table logic. So let's look at the table. It looks like they ran the reaction 3 different times. I've got my concentration of H2O2, of I minus, and then I've got the rate on the very far right. So now let's look at determining the order of this reaction with respect to hydrogen peroxide, H2O2. Remember, I want to look at the table and I want to find a spot where H2O2 is changing, but that the other 2 are constant. And if we look at reaction 1 and 2, that's what I would choose. Because H2O2 is increasing by a factor of 2 as we go from 2 to 1. And it's constant here, so this is my control. And let's look at the rate. How is the rate changing now? Okay, so let's look at that. And if you notice, 6.9 is larger than 3.4, and they're both times 10 to the minus 4. So let's take our larger one, 6.9, times 10 to the minus 4, and divide it by the smaller one, 3.4 times 10 to the minus 4. And what you'll notice is 2.03, but it's essentially times by 2. So it gets twice as fast. So now my table logic, okay, we filled out the table. Now let's see if we can determine the order. If we're timesing the concentration of H2O2 by 2, the rate also increases by a factor of 2. So in order to get a 2 here, what does the exponent have to be if we're putting a 2 in here? hopefully you're thinking to yourself that exponent has to be a 1, because 2 raised to the power of 1 is 2, which is what it equals. So it's first order with respect to H2O2. Okay, now let's erase that and clean up this table a little bit. And let's look at our other reactants. Let's go to I minus iodine. Again, we want to find a spot where we want to determine what the exponent is here. So what order this is with respect to iodine. We want to find on our table where iodine is changing, but that the other reactants are held constant. And if you look, iodine is changing between 1 and 3, and H2O2 is held constant. So we're increasing by a factor of 2 here, and this one's our control. It's not changing. Now let's look at what the rate is doing. Okay, they're both times, actually it's times by 10 to the minus 3 on the bottom. So this is actually a larger number. So when you put it in your calculator, because it's times 10 to the minus 3, this becomes a larger number. So 1.4 times 10 to the minus 3 divided by 6.9 times 10 to the minus 4. And that's 2.0289. So essentially we're timesing it by 2 again. All right, so now we can use this table logic. If the concentration of iodine is changing by a factor of 2, and the rate is also increasing by a factor of 2, what exponent would need to come here? And hopefully you're thinking to yourself that that number has got to be a 1. 2 raised to the power of 1 is 2, and that's what the rate changed by. All right, so let's erase that and figure out our last reactant. On our last reactant, we have H+. But you'll notice in our data table, it doesn't give us any data for H+. And when that occurs, guys, if it doesn't give you data, it's implying that it is a 0 order with respect to H+. So H+ does not have any influence. The concentration of H+ has no influence on the rate. And so if they leave it totally off, we can just assume that it's 0 order with respect to that reactant. All right, now let's clean this up and write the rate law. So the rate law is going to be rate is equal to K times the molar concentration of H2O2. Would I need to write this 1? No. It's implied. And then we times it by the molar concentration of iodine. Again, we don't need to write the 1, it's implied. And because hydrogen is a 0 order, anything raised to the 0 order is 1. So we can just leave it off. This would be the answer for the rate law. Okay, now quickly, we just need to find the rate constant, which is K. So let's do that over here. I've got a bit more room. So let me rewrite the rate law. It's equal to K times the molar concentration of H2O2 times the molar concentration of iodine. And now let's substitute in. Again, when we're doing the rate constant, you can choose any one of these experiment numbers. I always like to choose the top one. So my rate for this first experiment was 6.9 times 10 to the minus 4. That's equal to K, which I don't know, times the molar concentration of H2O2. So let's look at our data here. It was 0.1. We're raising it to the first power. And now let's times it by the molar concentration of iodine, which again was 0.1. And so now we can solve it. 6.9 e to the minus 4 is equal to K. And let's just do 0.1 times 0.1 in your calculator. You should get 0.01. Now to solve for K, I would need to divide both sides by 0.01. Over here it cancels out. And if you do that, 6.9 times 10 to the minus 4 divided by 0.01, I'm getting that K is equal to 0.069. Okay, and then if we wanted to determine the units for K, let's go back and look at the overall order would be 1 plus 1 is the overall order is 2. Remember, subtract 1 from that, it's equal to 1. But you got to put molarity, and then you've got to put a minus sign in front of that 1. So minus 1 seconds to the minus 1. And there's your answer. All right, guys, I know that's quite a lot to go through, and hopefully you understand now how to write a rate law, how to use table logic in order to determine the order of the reaction with respect to those reactants. And in the end, you can calculate the rate constant, K. To give you some more practice, this takes a while to kind of learn, but to give you more practice, I've got in your student workbook, there's a worksheet titled Rate Law Worksheet. So please go there now in your student workbook. Again, it's called Rate Law Worksheet. Let's get that done, and hopefully this video helped you.